Hello! In this section, we finally get to talk about polynomials, which is what the last couple sections have been building up to. So I guess polynomials, we'll see what the definition is soon, but we're going to want to, in the next couple sections, figure out what they are, how to add them, how to subtract them, how to multiply them, and how to divide them. That's what the next 3 or 4 sections are all about. But in order to learn how to, I guess, especially multiply and divide polynomials, you had to have known all those exponent rules. That's what the last couple sections have all been about. It's kind of leading up to, like I said, we're wanting to learn how to add, subtract, multiply, and divide these guys, but we wouldn't know how unless we knew all the exponent rules. But finally we get to see what these guys are all about. You've probably seen these before, I'd imagine, but if not, a polynomial, it's just an expression of the form, and this looks really complicated here, this thing after the colon in the sentence. But it's all it really is just think of these a sub n plus a sub n minus 1, a2, a1, a0. Those are just coefficients. So you're thinking of those guys, an minus 1, and there's a dot in the middle of that polynomial because you don't really know how many terms there are in the polynomial. There could be a lot, there could be very little. That's why that dot's there, just to say, I'm not really sure how many terms are in between the ones I've written here, but let's just pretend like we know, and however many there are, they would be in here. So these guys are the coefficients. And we'll see that, but of the variable. And then of course you have x's next to each of those a's. So here you have x to the n power, and n in these ones, n is always a whole number. Yeah, so you'll never see a negative exponent, even though we saw them in the previous sections. In a polynomial, you'll never see a negative exponent. And then here you got x to the n minus 1 power. Whatever n is, n minus 1 is some whole number also. And then all the way down, dot. And then you have your kind of smaller powers here, x squared, whatever. The next one's x, which you can think of as x to the 1. And the very last term, a sub 0, it doesn't have any x's. So that'll be like the constant term of the polynomial. And I know that looks confusing, but it makes a lot more sense when you see a concrete example. So here in this red box that I'm drawing, this is what an actual polynomial looks like. So notice you have coefficients, it's 3, negative 5 halves. The coefficient of the third term there would be negative 1. The next coefficient would be 0.9. And in the constant term, you'd have negative 1. So those are what the a sub n minus 1, all those, that's what they're referring to, just whatever the number is or the coefficient in front of the variable x. That's what you would say is the a subscript. And then the x, notice the power here, n would be 5 in this example. Because you see that your highest power in that polynomial is a 5. And then notice n minus 1, the next power would be 4. You're missing a third power, but that's okay. The next one's square. Now you have x to the 1 power. And then finally your constant term, there is no x attached. So that's really what a polynomial looks like. I think polynomials make a lot more sense when you see a concrete example like that. So yeah, to identify a polynomial, I guess it's just a bunch of terms adding or subtracting like we have here. One thing, subtract another, plus another, subtract another. It could have as many terms as it wants to, adding and subtracting. Some of the terms are going to have an x attached, one may not, the constant term, but x will always have an exponent that's a whole number, like 1, 2, 3, 4, 5, etc. On and on and on. It could be as high as you want it to go, but it will never have a negative exponent or a fraction exponent, nothing like that. And then your coefficients, they can really be anything. Notice you have a whole number for your first coefficient on the left, a fraction for your second coefficient, and then for your fourth coefficient over here you have a decimal. So it could be anything like that. It could be a whole number, it could be a fraction, could be a decimal. It's kind of a mixed bag, it could be anything. But it just can't be an imaginary number. If you're familiar with imaginary numbers, you won't see those in polynomials. Okay, that's what a polynomial looks like. And a lot of what makes polynomials complicated is just the terminology. So here we have kind of a list of these definitions that you don't really need to memorize them. I mean, it's not like on the next exam I'm going to say, what's the definition of degree, or what's the definition of binomial, and nothing like that. It's just, that way if you hear them referred to as that term in the book or on these videos, you'll know that, oh, okay, I remember what that means. So it's just really so you can use the terminology and understand the terminology. So how about we'll practice. We'll say, looking at each of those definitions, let's refer to this example we have here and see if we can figure out what all those definitions are when it comes to this one example, the 3x to the 5th minus 5 halves x to the 4th, etc., etc. So here for the first one, the first definition says that we've been saying this word term over and over, so I think we kind of already have an idea of what term is. The terms of a polynomial are the things being added and subtracted. So in the above example, the terms are, the first one there is 3x to the 5th, and then you're subtracting, the next term would be, I guess you want to technically, if it's a subtraction sign in front, think of it as a negative. So I'm thinking of the second term as not just 5 halves x to the 4th, I'm thinking of it as negative 5 halves x to the 4th. The third term is negative x squared. The fourth term is 0.9x, and the last term is negative 1. So just, really it's the things that are being added and subtracted together here, they're separated by pluses or minuses. Okay, so those are terms. What else is there? Then the next definition, it says that the degree of a term of a polynomial, it's just the exponent on the variable. So how about for each of these terms that we wrote in the last definition, let's see what we think their degrees are. So for the term 3x to the 5th, as it says, the degree is just the power on the exponent, so it'd be a 5. And in the second term, the exponent is 4, so the degree would be 4. For the third term, the exponent is 2, so the degree would be 2. For the second to the last term here, there is no exponent on x, but remember, if you see a variable with no exponent, it's automatically a 1. So if you want, you can add a little 1 exponent there, just to remind yourself. And then the last term, notice there is no x, so if you're looking for the degree of that term, you're supposed to be looking for the x and looking for its exponent, but if there is no x, how can I look at it as exponent? We just say that if there is no x, we're going to say it's an exponent of 0. Because there's no x. Okay, so those are the degrees of each of those individual terms. Let's look at the next definition here. It says the coefficient, we've been using that word over and over too, so you probably already know what that means. The coefficient of a term of a polynomial is the constant factor in front of the variable. So it's really just the number that's in the front. Okay, so if we look at those terms that I wrote in the first definition, the first term is 3x to the 5th, its coefficient is 3 because that's the number in front of the variable. For the second term, you got negative 5 halves x to the 4th. Its coefficient is negative 5 halves because that's what's in front of x. The third term, negative x squared, its coefficient would be negative 1 because it's a negative, and then also since you don't see a visible coefficient, it's automatically a 1. The second to the last term here, the coefficient is 0.9 because that's the number in front of x. The last guy, even though he doesn't have an x, we say that the coefficient is negative 1, the number itself, since it's constant. There is no x next to it, but if there was an x, that would be the number in front of x. All right, that sounds good. So those are the degrees of each of those individual terms. Or sorry, not the degrees. We did the degrees. This is now the coefficient. Sounds good. How about we'll look at the next definition here, the degree of a polynomial. So notice, they look like they would be the same. The second definition says, what's the degree of a term? So that you're only looking at one individual term of that polynomial. Like say if you focus on the first guy, 3x to the 5th, you say, what's his degree? Whereas if you just say in general, what's the degree of that polynomial? All that is they're asking what's the largest exponent. So you're looking at that polynomial, what are all the exponents there? It had a 5 first, then a 4, then a 2, then a 1, then a 0. The largest of those is 5. I could have looked at all these green numbers here, right? Those were all the degrees of the terms. The largest of those was 5. So that's what we'd say. We'd say this is a degree 5 polynomial, or a 5th degree polynomial. Let's see, then the next definition, these ones you probably won't use as much, but they're, just in case you see them, you'll know what they mean. A monomial, if you think about the prefix mono means 1. So a monomial is a polynomial with only one term. Oops. There's a E in the word 1, isn't there? Oops. Sorry. That should be only one term, not only on term. That doesn't make any sense. So what's a monomial? Yeah, it's just, imagine you had a polynomial, which poly is usually multiple, which seems kind of confusing. Why would you be talking about monomial with 1 when poly means multiple? But anyway, don't worry about it. A monomial, it's a polynomial with only one term, so we can make up an example. Let's say, for sure the example we have above, the one here in this blue box, that is not a monomial. That polynomial has how many? 5 terms. It's not a monomial. It would have to have only one term. Let's see, something, I guess you could just grab one of those terms. Let's say negative x squared. That's an example of a monomial. It's just one term. It's not adding or subtracting with anything else. Or even a constant, you can say 7 is a polynomial, or sorry, a monomial. It's just one term. It happens to be a constant term. Or you can make it more interesting. How about like 1,247 x to the 37th power? That's fine. That's a little more interesting, but as long as the number in the front is a real number, not imaginary, and the exponent's a whole number, like 37, that's a whole number. It's a large whole number, but it's still a whole number. That still technically counts. You probably won't see monomials that large, with that large of a coefficient and that large of a degree. But, we can get ridiculous if we want to. The next definition, a binomial. Also, that one, if you think about the prefix bi means 2, the number 2. So it makes sense that a binomial is a polynomial with 2 terms. So those ones are fairly simple looking, not quite as simple looking as the monomials, of course. But you can have, let's say, something as simple as x plus 3. That's a binomial because it has 2 terms, x and 3. Or you could do, I don't know, trying to be creative here, 4x cubed minus, I don't know, 11x to the 10th. Sure, those are just 2 terms. You can make up whatever coefficient you want. It could be a fraction, it could be a whole number. Then you can make up any exponent you want as long as it's a whole number. So as long as there are 2 terms, then you got a binomial. The last definition there is kind of what you would expect it to be, a trinomial. Tri, of course, means 3, so that would be a polynomial with 3 terms. Like, let's say x squared plus 5x minus 6 or something. That's a trinomial. Or, I don't know. You could be as crazy as you want. 18, I don't know, minus 4/3 x to the 13th plus, I don't know, a decimal 0.07 x to the 9th. Whatever, that's complicated looking, but there's still technically only 3 terms. 18 is one term, the 4/3 x to the 13th is the second term, 0.07 x to the 9th is the third. I like the first one we did a lot better. It's a lot simpler, but still technically both are just trinomials. And then from there, if you have a 4-term polynomial instead of a 3-termed or a 2-termed or a 1-term, we don't give it a name. We only give names to 1-term polynomials, 2-term polynomials, and 3-term polynomials. It'd get ridiculous giving a name to every, 4 terms, 5 terms. Nah. After 3 terms, we'll probably just say, oh, it's a 4-term polynomial, or it's a 5-term polynomial. Yeah, so there's no names after trinomial, that's it. All right, so that's really, this section's all about introducing us to polynomials. And then the examples we have, they're fairly simple and you'd probably guess how to do them. So I think you're going to like them. Let's see. So example 1 says, evaluate the above polynomial in the evaluate the polynomial in the example above for x equals -2. And by that, I think we're referring to that example that we boxed in blue there, the 3x to the 5th minus 5/2 x to the 4th minus x squared plus 0.9x minus 1. So we're going to take that and do probably exactly what you're thinking of doing. We're going to replace all the x's with -2. So where any x was, here's an x, I'm going to replace it with -2. Here's an x, and here's an x. There's only 4 x's. But everything else around them is going to stay the same, the coefficient, the exponent, all that stuff. And I'll just try to evaluate this as best I can. Try to be really careful because I'd probably make a mistake if I'm not careful. And I should be able to get this down to one number. And keep in mind too that you have to use order of operations, so I should look at anything in the parentheses first, then exponent, then multiply or divide, then addition or subtraction. But within each of those parentheses that I put, there's nothing really to do. It's just a number there, -2. So I don't really need to do anything in parentheses. But there are a few exponents here. I better take care of those. So here I have -2 to the 5th. Maybe we can kind of think about that off to the side here. -2 to the 5th. That's -2 times -2. 5 -2s. That's a lot of them. So let's see. The first 2 multiplied together, -2 times -2 is 4. That times the next -2 is -8. Okay, I'm going to keep that in my mind. -8 times the next one would be -8 times -2, that's +16. +16 times the very last guy, positive 16 times negative 2 is negative 32. So that would be what we're left with here as negative 2 to the 5th. And for now, I'm just going to leave the coefficient of 3 the same. And I think while I'm at it, I'm going to evaluate what this is here, the negative 2 to the 4th, and also this negative 2 squared. And there's no exponents left in the rest of this thing, so I'm just going to leave it all the same. But how about this negative 2 to the 4th? I think I kind of did that halfway through when we were looking at negative 2 to the 5th, huh? It was negative 2 times a negative 2. That's 2 of them. That's 4. 4 times negative 2 is negative 8. Negative 8 times 1 more 2. Negative 8 times negative 2 is positive 16. So that would be negative 2 to the 4th power. And then next we're raising negative 2 to the 2nd power. That's negative 2 times negative 2, which is positive 4. And keep in mind, since you're squaring a negative, that guy goes away because it's a negative times a negative, which is a positive. But the negative that was in the front of the parentheses is not affected by the square, since he wasn't in the parentheses. Okay, that looks good. Now we'll just kind of go ahead and multiply everything since we're done with the exponent portion. Let's see, the very first term, you have a, see, I'll highlight it here. We got 3 times negative 32. We'll look at that guy first. 3 times negative 32, I believe, is negative 96. Alright, and the next term, I better be really careful here. I've got a fraction times a whole number. Let me put that whole number over 1. And then I can reduce a little bit. I got 2 going into 16. That goes in 8 times. So this whole second term ends up being the 5 in the front times the 8 that I'm left with here. That's 40. And it's negative because there was already a negative sign in between the two terms. So I got that. And then the next term, there's nothing really to multiply. It's just a negative in front of a 4. So I'm just going to keep it as negative 4, but I don't really need the parentheses. I'm going to drop them so I don't confuse myself. And then the next guy here, we got 0.9 times negative 2. That's going to be negative 1.8. Running out of room. And the very last term is just a constant, so I'll leave him the same, negative 1, or minus 1. Okay, let's see. Now all we have to do is combine all these guys together. And the way I like to do it, I don't know about you guys, but I'll do 2 at a time. Like, okay, what's negative 96 and negative 40? Negative 96 minus 40 makes negative 136. Negative 136 and negative 4 together make negative 140. Negative 140 and negative 1.8, that's negative 141.8. Negative 141.8 minus 1, negative 142.8. Wow. That was a lot of work, but there it is in all its glory. That's the answer to that problem. And you don't have to do that very often because polynomials can be really large and evaluating them can be tedious, as you see in this example, because there are a lot of x's to evaluate at different exponents. So really, in practicality, usually we use the large graphing calculators in real life to do calculations like this. So if you own like a Texas Instruments 82 or 83 or 84 or 89, those guys can do that for you. So there's, in case you're curious, if you're thinking, is this really the best way to do it? There's a place in those complicated calculators to input the polynomial. You have to kind of type it in, and then you're going to give it x equals negative 2, and it'll spit out this number for you, like almost instantly. So it's good to know, what the calculator is doing because, you guys, I don't know if you've ever seen the movie Terminator, but Terminator happens when the robots and the computers get smarter than us. We definitely don't want that to happen, you guys. So I got to make sure I know what the calculator's doing, I'm going to show it who's boss. I say, all right, calculator, I know you can do this calculation faster than me, but I know exactly what you're doing. Look, I did it too. So don't be trying to take over. Sheesh, Okay, that's a little extreme of an example, but hey, you never know. Terminator could happen, right? Watch out. I don't mean to scare you guys. I'm sorry. All right, let's look at this next example. They say they want us to combine like terms and write your answer in descending order of exponents. So you might have already heard someone say this before, but when you combine like terms, you say, okay, which guys are like terms? When you end up writing it in the end, you want to write the term with the highest exponent or the largest degree on the left side, and then continue going smaller and smaller until the very rightmost term is the smallest degree. So probably when I look at these guys, like, let me focus on part A here. I'm going to look at all the exponents. Okay, where are all the exponents here? We got a second power, a third power, another third power, another second power, another second power, and then a fourth power. What I'll do is look for the largest power and see if he has any like terms. So it looks like this negative x to the fourth, that's the highest power I see. If he had a like term, I would combine them, but there is no like term, so he'll just stay as is, negative x to the fourth. And the reason I focused on the largest power is because I want to make sure I write the largest power on the left, and then from there continue getting to smaller and smaller powers. So after x to the fourth, the next largest power would be x to the third. I have two of them here. You have a 2x to the third and minus 3x to the third. And if you remember, when you're combining like terms, you do not change the exponent, you only add or subtract the coefficients. So keep that in mind if you kind of have forgotten that or you never knew that. When you're adding or subtracting, you don't change the exponents. You know, all the exponent rules that we had in the previous sections, they were only there for when you're multiplying two terms together, not adding or subtracting. But we did talk about multiplying and dividing terms, but never adding and subtracting. So you don't want to change the exponents, just combine coefficients. That's the only thing that's going to change. Alright, so I'm going to keep that in mind. Looking at those x cubed terms, I'm just going to look at the coefficients there. And it doesn't really matter what happens, but I know that the power on x is going to stay a third, or a third power. All I have to do is say, what's 2 and negative 3 put together? Well, it'd be negative 1, but I don't really need to put the 1. I can just put a negative, because we know if you put a 1 there, you're going to want to simplify it and write it without the 1. So I think those look good, and then what other terms are left? I think the only terms left that I haven't looked at yet are the 10x to the second power, negative 4x to the second power, and negative 6x, negative 6x to the second power. They all have the same power, so I think I'm able to combine those guys. Let's see, and when I do, they're all going to be x squared, right? Something x squared. But all I have to do is combine their coefficients, so starting with the 10 on the left, I take 10 and I subtract 4, that's going to be 6. But check this out, when I subtract 6, I'm going to get 0! So they actually cancel each other out. You could put a 0 if you want, but 0 times anything is 0. And then that term will just disappear. So really what you're left with is just the negative x to the fourth minus x cubed. Those are the only guys that kind of stuck around and stayed with it throughout the whole problem. That one really got very simple, huh, when we were finally done combining stuff. So we did it. Alright, that's the answer to part A. Let's try part B here. So part B, I'm going to try to do a similar thing. I'm going to look for the highest power there. Looking at all these terms, I think x cubed has the highest power, right? And there's two of them here. You have an x cubed and another x cubed. But I'm not excited that they have fraction powers, huh? Ugh. Well, I think I might have to do a little more work here, because I know if I want to combine this guy, 1/6 x cubed, and the next guy, 1/3 x cubed, I know that the x cubed won't change, but the coefficients will change. I have to subtract them. But in order to subtract them, we know if you're subtracting or adding fractions, they have to have the same denominator. So looking at those guys, the common denominator would be 6. That means I'd have to multiply the second fraction by 2/2. Let me write that out real quick. I might write out more steps than than someone else might, but couldn't hurt, right? So okay, the first term I'm keeping the same because it has a good denominator. Second one, though, becomes now 2/6 x to the third. And I think I'm going to run out of room here, so I'm going to write it down here. I have 1/6 minus 2/6, that's going to be negative 1/6. Then you're keeping the x cubed the same, as we said. Alright, so we took care of the x cubes. Maybe I'll color code it so we remember where he came from. He came from the two blue ones combining. And I'm looking at what I haven't combined yet. The next highest power is a square. I see a 3x squared and a regular x squared. Those are probably going to be the next guys to add together. Although those ones, I don't know if I really need to be as careful as the last time. You just have 3 of them here, 1 of them here. That's a total of 4 of them, 4x squared. And keep in mind, like we said, you're not going to say, oh, x squared plus x squared is x to the fourth. You don't add powers when you're adding terms. You keep the powers the same. Alright, so we got that term, and then all that's left here is a couple constants, and of course a couple constants can combine. So look at those guys here. We got a 7 and a negative 10. Positive 7 and negative 10 makes negative 3. Should have chosen a different color here, huh? Oops. How about, we have any pink? Everybody loves pink, come on. 7, and a negative 10 together makes negative 3. There we go. So the last term will be negative 3. Beautiful. I love it. The color is beautiful. Okay, calm down, right? Calm down. It's not that exciting. So there it is. And it's up to you kind of how much work you want to show. I don't know. It's not necessary to show as much work as I do, I guess, but I guess it couldn't hurt. All right, this is a very short section, huh? It's just as long as you're careful, you should be fine. So the last example we have here is just, I guess, a real-life situation of where you might see a polynomial. It's hard to believe that these things are useful in real life, but this one's kind of interesting. And forgive me if I mispronounce this word. I have no idea. So you got this antibiotic, gentamicin? I don't know. I'm assuming that's how it's pronounced, but please don't make fun of me. Gentamicin is an antibiotic frequently used by veterinarians. So interesting, okay. The concentration in micrograms per milliliter of gentamicin in a horse's bloodstream T hours after injection can be approximated by this polynomial. Okay, so they're saying whatever you input for T, I mean in this one they have a T, but in the last example we had an X. It doesn't matter. If you replace T with 5, let's say, and you simplify this all the way down like we did in the previous example, it's going to tell you how many micrograms per milliliter of this medicine is still in this horse's bloodstream after 5 hours. So I guess, yeah, like it says, T is the number of hours that have passed. And then if you plug it in for all the T's there, it's going to tell you how much medicine is still left in their system. So it's kind of interesting. I think I remember that I got this problem out of the book, and you don't really need to know this part for this problem, but the graph of this guy, it kind of went, let's see, how did it go? It started off at 0, because of course before you even inject it, the horse is not going to have any medicine, but once they injected it, it spiked, it started running through the horse's bloodstream. But at a certain point, it kind of peaked, and then it slowly went down, and it kind of, it went away from their bloodstream. So that's interesting that this polynomial has a graph that looks something like this. Interesting. So it's kind of like the horizontal axis is time. So as time went on from 0 on to, I'm not sure, I can't remember how many hours it stayed in the bloodstream, it went down. And this is the y-axis is the concentration. Because it started out at 0, and it went up to whatever the peak was, some high, I can't remember, and then it went down again to 0 eventually. Okay, so what do they want us to do here? Part A, find the concentration of this medicine in the bloodstream 1 hour after injection. Alright, so it already said that if you want to figure out how much of this medicine is still in the bloodstream after T hours of injection, it says just replace all the T's with that number. All I have to do is take the right side of that equation, the polynomial portion, and replace all the T's with the value they gave us, 1. So I'm just going to rewrite that guy, kind of leaving blanks where all the T's are, and then I'll replace all those blanks with a 1. And if you're looking ahead, you can see that part B is very similar, except you're going to be replacing T with 2 instead. So if you want to, you can already start setting that guy up too. It's going to be the same thing. We're going to do the exact same calculation, except T is going to be replaced with 2. Because in part B, they want to know how much of this medicine is still in the bloodstream after 2 hours. So you can kind of set up the blueprint here of what this is going to look like, and then substitute the values. So first one we got, or part A was 1 hour, so I'm going to put a 1 in there. 1, 1, 1, 1. And then part B, we'll put a 2 in for all the T's, because they want to know after 2 hours. So I'm just going to focus on the first one, or part A first. So I like part A because I know that 1 to any power is 1. That's my favorite. So 1 to the 4th power is 1. 1 to the 3rd power is 1. This is awesome. 1 to the 2nd power is 1. Best day ever. 1 to the 1 power is 1. So now it all comes down to multiplying each of those coefficients by 1. And you know what happens when you multiply something by 1. The thing is unchanged. Multiplying by 1 doesn't change anything. So really this comes down to you're just adding the coefficients. Negative 0.005, 0.003 added, 0.35, and then 0.5. And that, I don't know, I'm kind of worried that I won't line up the decimals correctly if I do that. So I might think about that over here on the side here. So maybe I'll combine a couple of them at once. Well, the first guy is 0.005, and it's a negative, and you're adding it with 0.003. So really you can think of that as 0.003, the positive one, subtracting the negative one. Okay, if I subtract those guys, that's negative 0.002. So that's the first two combined. I've got those guys covered, and I have to add the next guy. 0.35. What if I add 0.35? Well, I don't like to see a negative on the top, so I'm going to switch those guys around. Think of that as 0.35 because it's positive. Subtract 0.002. I'm going to have to do some borrowing here, especially in giving this guy a 1 or 0. I need to borrow from the 5, make him a 4, and make this a 10 here. Then I'll have 0.348 if I subtract 10 minus 2. That's the first 3 terms combined. Now the very last guy, I just need to add 0.5, and then I'll be done. That's 0.848. Okay, so that must be the guy. 0.848, and this is, I guess, what's the units here? What is it? Micrograms per milliliter. Micrograms per. There we go. And that's after 1 hour. Didn't really leave myself a lot of room for full sentences here, but you could say the horse has. That's enough. Yeah, the horse has that many micrograms per milliliter after 1 hour. Sure, why not? That sounds fine to me. And let's see, it's going to be a little more complicated to simplify the second one, because in the last one we had 1 to a bunch of powers, that's always 1. But here, 2 to a bunch of powers is not always 2. So I got 2 to the 4th power, 2 times 2 times 2 times 2 is 16. And then 2 to the 3rd power, 2 times 2 times 2 is 8. 2 to the 2nd power is 4. And then of course 2 to the 1 power is 2, so he'll stay the same. And then I'm going to have to, the next step would be multiply the coefficients by each of these blue numbers that I just wrote, the ones that resulted from the exponents. Alright, looking good so far. So let's see, I might have to, this is kind of a tedious part, huh? I have to go off and try to figure each of these out on the side here, or kind of toward the bottom. I'm going to focus on this guy first. What's 16 times 0.0, I want to line them up better. 16.005. There we go. So for now I'm going to ignore the zeros. I'm just going to say, what's 5 times 6? That's 30, carry the 3. 5 times 1 is 5, plus 3 is 8. And then I got to keep in mind, okay, there are 3 decimal places here beyond the, there are 3 digits beyond the decimal. So I better do the same thing in my answer. 1, 2, 3. So it must be 0.080. Or you could, if you want, since that number on the, or the digit on the right is 0, you can just drop that guy and make it 0.08. That 0 there is not really necessary. So that's that guy. How about the next guy? It's going to be a little easier. And think about that guy down here too. It's 8 times 0.003. So all we really have to do is think about what's 8 times 3. Okay, that's 24. But I should see 3 digits beyond the decimal. So I need to move the decimal 1, 2, 3 times, which will make it 0.024. That's the next term. We're almost getting there. The next one, at least the numbers are getting a little nicer. The next guy looks like 0.35 times 4. So I'll go 5 times 4, that's 20, carry the 2. 3 times 4 is 12, plus 2 is 14. And I only see 2 digits beyond the decimal here, the 5 and the 3. I need to take my decimal and move it twice. Aha, so it's 1.40, but you don't really need the 0. I'm just going to write 1.4. Oh, you know what, you guys? What did I forget here? I forgot this negative. Hello. I went off and multiplied the 0.005 by 16, but I forgot to carry the negative. That could have been deadly. Ooh. Anyway. And then 2 times 0.5, that's going to be a 1. That one. I always remember that because that's like 0.5 is the same as a half. Half times 2 is 1. Okay, I think we're doing good here. Let me try to go ahead and combine some stuff. What's 0.08 plus 0.042? I want to be careful here. I'm going to think about that down here on the right side. It's really, if you think about a negative adding with the positive, you can take the positive number and subtract the negative number. That's probably easier. Alright, since everything doesn't line up, I'm going to put a 0 here for the 8, just so everything lines up. 4 minus 0 is 4. Let's see, no, you can't do that, huh? Uh-oh. I better subtract it the other way, sorry. Let me go the other way. Because you can't subtract 24 from 80, right? Or I mean, you can't subtract 8 from... So I better do it the other way. 0.08, because that's larger. 0.024. And subtract those guys. I'll just keep in mind that the answer is going to be negative, because this is a larger number than this. 0.08 is larger than 0.024. So when you add a large negative with a small positive, you're going to get a negative in the end. Okay, let me subtract these guys. Putting a 0 there, I'm going to have to borrow from the 8, make that a 7. This guy will become a 10, and if I subtract, I'll be left with 6. 7 minus 2 is 5, and then the zeros, you can still get a 0. So it should be 0.056 for those two combined. And again, it's negative because you're taking a large negative and a small positive. When you combine them, it's going to be a negative. And then I'll try to add 1.4 with that guy. Or you know what? These might be easy to add right now, huh? 1.4 and 1, that's just 2.4. Might as well combine those guys. And then the last step would be take 2.4 and subtract 0.056. So that'll be my last step here. I'm going to write that 2.4 minus, I'm going to try to line up the decimals here. 0.056. Well, I don't see anything to subtract the 5 and the 6 from, so I better put zeros. And I have to borrow, make that 4 into a 3, make this a 10, but then I need to borrow from that guy, make it a 9 and make this a 10. 10 minus 6 is 4, 9 minus 5 is 4, 3 minus 0 is 3, 2 minus 0 is 2. So it should be together, finally, 2.344, and this was measured in, was it? Micrograms per milliliter. So I could say after 2 hours, the horse had that many micrograms per milliliter of the medicine in his bloodstream. You could just leave it at that, though. That's good. Whew. All right, that was a lot of work, you guys. But that's, I guess, in real life, yeah, you'd probably use a calculator to calculate all that. But it is good to know. Again, I want to be smarter than the Terminator. I mean, no. Was Terminator a good guy or a bad guy? Good guy, right? Anyway, I want to be smarter than Skynet, the company that made the bad guys, the bad robots. Okay, so that was that. I think these next couple sections should be pretty short, so it'll reward you for sticking with all these longer sections and kind of tedious sections. So thanks for listening. I'll see you, and we'll have a good time in the next couple sections.